Our speaker this evening has been working in IT since, get this, 1984. That is a whopping 34 years. He has when he started. Kind words. All right, he has been with Sun Microsystems since 1996, followed through to Oracle through that acquisition, and is also a Java champion and was awarded Java Rockstar status through Java 1. Please welcome the Deputy CTO of Azul Systems, Simon Ritter.
Right, thank you very much. Good evening. So, I guess from the answers that I saw people giving that some of you use Java. Who uses Java? Okay, good. We're in the right room then. Excellent. So what I'm going to talk about is how you can make Java faster. And the theme of the evening is more about sort of big data and streams and processing data. So I thought, okay, I'll call this faster Java without pauses for stream processing. First thing we need to look at is what do we really kind of mean by this, and what is the impact if you're writing Java code. So big data. Okay, big data means we need a big heap. Now, one of the questions was how big can the Zing JVM actually support in terms of heap size? And the answer was 8 terabytes. So we'll come back to that, but that is a big heap. And if you try and use other JVMs with a heap that size, you are going to end up with very long pauses. I was talking to a customer that we had who had a heap size that was so big that they were getting pause times for garbage collection, which were very big. So who's seen pauses of like a few seconds for their JVM? Okay, anybody seen like a pause of like maybe a minute or a couple of minutes? Okay. Anybody seen like 20, 30-minute pauses? Okay, one person over there, yeah. Okay, well, so they were having a pause of 1.5 days for a garbage collection. And I must admit, I spoke to them and I said to them, okay, so in 1.5 days, how do you even know that it's still doing garbage collection? And they said, it's okay, we have JMX, we monitor it, and we know that it's actually doing things. And then I said, okay, so you know it's still doing garbage collection, but why don't you just like stop the JVM and restart it? And they said, no, it actually takes longer to load up all the data than it does to do the garbage collection. So that's why they were talking to us. So big data means big heaps, and like I say, typically that means long garbage collection pauses. If we're talking about streaming, then what we're talking about is something that's much more compute intensive. We want to process the data, we want to do something with it, and ideally we want to do it in parallel, because we're talking more about sort of functional style of programming, where what we're going to be doing is dealing with individual pieces of data. We don't need to necessarily relate the data to each other. So how do we optimize the JVM to get better throughput of our data in that sort of situation? So the first thing we need to talk about is what do we mean by speed in terms of the Java world? Because obviously you can write an application, and the way that you write an application is going to have a big impact on how well the application performs. You can write a bad application or you can write a good application. But then, whatever you're running runs on top of the Java virtual machine. And this introduces another layer of stuff that goes on. So we need to think about how does that kind of work in terms of speed. So I put together this really complex graph which shows what you really want in an ideal world for the performance of your Java virtual machine. And ideally, what's going to happen is, well, as soon as you start your Java virtual machine is going to go up to 100% of its performance, and it's just going to stay there. So you get a nice flat line, and it's always giving you exactly the same level of performance. Problem is, Java doesn't do that. JVM, the way that it's been designed, will not give you a nice flat line like that. What you tend to see is something more like this. And so when you start your application off, what you're going to see is bytecodes being interpreted. This is the whole idea of a Java virtual machine. It's not a real machine, it's a virtual machine. Those bytecodes have to be taken by the JVM, they have to be interpreted into the write instructions. That's how we get this lovely write once, run anywhere kind of idea that Java has always had from the beginning. Many people refer to it as write once, test everywhere. So we start off in interpreted mode, and then to improve performance, we compile some code, and we use a thing called so we start with interpret mode, then we switch to what's called the C1 JIT compiler. And I know that some people know what JIT stands for because that was one of the questions before we started in the quiz. So we have a just-in-time compiler that takes the bytecodes that are being used regularly, so if you've got a method that you call in a loop, and it will compile that into native instructions. C1 compiler is designed to do that very quickly, so you want to get the compiled code as quickly as possible, but it won't optimize it very heavily. It will just do a straight compilation of that code without doing anything special to it. So we get a bit better performance. Then we optimize based on some profiling data. So we watch that method as it's being used and we see how it's being used. And then we can recompile it using a thing called C2. That's another JIT compiler that does do optimization, and it will make a lot better attempt at providing better code, and so you'll see that the code will start to improve in terms of its speed. But one of the things that JIT compilers do to give you really good performance is they have these things called speculative optimizations. And the easiest way to understand that is that if you have an if statement in your code, which I'm sure many of you do, and you've got two branches from that if statement, there may be a situation where you run your application and it always goes through one branch of the if statement. So the compiler will notice that, and it will say, okay, when we compile that code, let's compile based on the assumption that it will always continue to go through that branch of the if statement. That way it can do certain things to improve performance. But of course, if at some point something strange happens and then it goes through the other branch of the if statement, the compiler has to say, I made a mistake, I have to throw away that code, go back to interpreted mode, and then reprofile and recompile. And that's what's called a de-optimization. So this is where you see like drops in the performance as you go through optimization, de-optimization, and then you get to a steady state. So you get to a steady state, but then you still see that there are drops in performance. Where do they come from? Those are your garbage collection pauses. So the longer the bigger your heap, the longer your pauses are going to be. So the question is, what if there was a better JVM? What if there's a better way of doing this, where you didn't get all these effects of the performance? And the answer is, there is. It's called Zing. So what does Zing do that's different? Well, what we do is we essentially take the same source code that other people use. So Oracle use it, IBM use it, Red Hat use it, lots of other people use it. This is the Open JDK, open source, released under a GPL v2 license with class path exception. And we use that to start building our JDK. So we're starting from the same point. We run all of the standard tests on that, so even though we make some changes, we still run all the tests, we pass all the tests, and we make sure that it is a drop-in replacement for a JVM. So you don't have to change any of your code to work with Zing. The only thing you might have to change is some of the flags you use when you actually start the JVM up, but in terms of coding, nothing has to be different to using from other JVMs. What we also do is we make some changes inside the JVM. So rather than having the parallel collector, the CMS collector, the G1 collector, and so on, we only have one. We have a thing called C4, and it's non-explosive. It's something which is a much better way of doing garbage collection. I'll explain about how that works in a moment. This also works in conjunction with some other things we have, which are called the Zing system tools. Then we replace some of the JIT compilation. So rather than using the older C2 style of optimizing compiler, we now have a thing called the Falcon JIT compiler. And the reason we call it Falcon is because Falcon is the fastest animal on the planet. So we figured this is the fastest JIT compiler on the planet, we will call it Falcon. And then, to help you with the idea of this warm-up phase, where you have to go from the graph that goes up to our steady state, we have a thing called Ready Now, which allows us to record information about a running application so that when you start it up again, you can start it with information that allows it to start at a much higher level of performance than if you started it off cold. Zing system tools. So I mentioned this briefly on the previous slide. What does Zing System Tools do? Well, if you think about an operating system like Linux, because that's the operating system we support, that has a virtual memory system, and that enables you to use the physical memory with different processes without having one process overwriting the memory of another. So virtual memory, physical memory gets mapped by the operating system. But the thing is, that's been designed to work with a very wide range of applications. JVM is a very specific application. And what we've done is we said, okay, let's take that idea of the virtual memory system and how it works in the Linux kernel and rework it just for the JVM. And that way, what we do is we can know certain things about how the JVM uses memory, and we can enhance the memory that it gets access to. So things like cache status. Zing System Tools will enable us to give hot pages to the JVM rather than cold pages. That way you get better performance in terms of what you're using for things like thread local allocation blocks and so on. This is very different, like I say, to a standard JVM. So we don't do the same things that other people do. The other thing is that we can return memory to the operating system, and that way we can share it amongst multiple JVMs. We can do better things that way. We also have some other interesting techniques that we do, which I don't have time to go into, but there's things like quick release, which means we can actually decouple a physical page from a virtual page, even though the virtual page is still technically being used, but it enables us to run the heap size or heap usage all the way up to almost completely full. We literally need only one free page of memory, physical memory, per garbage collection thread to do a full garbage collection cycle. Only one thing about this is we don't support any other operating systems but Linux, so there is no Windows version of this. Right, how does C4 work? Well, C4 stands for the Continuous Concurrent Compacting Collector. And obviously the name describes exactly what it does. So it is continuous, it runs all the time, so you don't get garbage collection that runs at certain times and not at other times. It's always sitting there in the background doing something. It is concurrent, and that's really important because it means you don't get pauses for garbage collection to happen. So garbage collection goes on at the same time that your application threads are making changes. And that's something that other collectors don't do. And it is compacting, which means we squash everything down to eliminate the spaces between data and eliminate fragmentation, so we can again get better performance that way. In terms of the basics of the C4 way of doing things, it is still a generational heap space. So this has been proved to be a very good way of doing things, having a young generation and an old generation. If you look at the way that pretty much any application works, you'll find that most objects that you allocate only live for a very, very short space of time. So by allowing objects to die young and die in the young generation, you can reduce the amount of work in promoting them to the old generation and having to do garbage collection on the old generation as well. So having two generations for your heap space makes a lot of sense. It is concurrent, as I said, so it runs at the same time as your application threads. It's also parallel, which means we can do multiple pieces of work at the same time by using multiple threads running on multiple cores. And it compacts the data so that we eliminate the fragmentation. There are lots of different algorithms that you can use for garbage collection, and one of the ones which is very common is CMS, the Concurrent Mark Sweep Collector. What we do is something that's kind of similar to that, but we have three slightly different named phases. So we have a mark phase, we have a relocate phase, and a remap phase. The big difference, which allows us to have true concurrency, is that we use a thing called a read barrier. So we nicknamed this the loaded value barrier. Every time you want to access an object, we will intercept that access and we will make sure that what you get back in terms of the reference to the object is correct. So we test absolutely every single object whenever you reference it. By doing that, we can enforce two rules on how the JVM works. The first is that whenever you're in the marking phase, so we're looking for objects that are still alive, whenever you access an object, it will always be marked as live. So that's fairly easy, not too difficult. But when we're doing the relocation and the remapping phase, we guarantee that the reference you get will be to the correct place where that object is. So if it hasn't been moved, it'll point to the old place. If it has been moved, the reference will point to the new place. That way you don't get any problem of updating an object in the wrong place and getting inconsistent data. So we eliminate that problem. This allows us, as I said, to do this completely concurrently. We can have application threads that run, application threads that are still making changes to objects, they're still creating new objects, at the same time that the garbage collector is running. And that's really the key difference. The way we do that is by intercepting every read to an object, and we do a very simple test. We do two instructions, which is a test and jump. So we use the object header, we use some bits in the object header, and we look at those to see what state we're in and whether we need to do anything. And then if we do, we jump to a handler, do some work, and then come back again. If we don't need to do anything, we just return the reference and off you go. Now, some people say to me, well, hang on, doesn't that mean that if you're intercepting every read to an object, that's going to degrade performance because suddenly you're placing this overhead on every object reference? And the answer is, well, in theory, yes, we are. But two instructions, if you look at the typical Intel architecture, that will actually equate to one micro operation. So a test and jump can be done in a single micro operation, which means every reference to an object is increased in time by roughly 1 nanosecond. So it doesn't really impose any significant impact on performance. Big heaps, no problem. We can scale all the way up to 8 terabytes. It used to be only 2 terabytes, and then we found another 2 bits in the object header. It's kind of weird that you need to find 2 bits to go from 2 terabytes of heap space to 8 terabytes of heap. We actually have customers who want us to go even further, and so now we have to find 1 bit so that we can double the size and go up to 16 terabytes. But finding 1 bit is actually proving to be quite difficult. Even with 8 terabytes of heap space, it doesn't degrade the performance of the garbage collector. You won't get long pauses when it has to run the garbage collector. This is really good because what it means is rather than having to divide your work into lots of smaller JVMs and keeping it into small heap spaces so that you minimize the pause times, you can just say, put all your big data into one big heap, and then you don't have to worry about garbage collection pauses. Zing does work very well with big heaps, but you don't actually have to have a big heap. So I know we're talking about big data this evening, but one of the things is you don't have to have a big heap. You can go from 1 gigabyte all the way up to 8 terabytes. Now, how do we actually show that this works? And I've spoken to a lot of customers about this. And one of the things that they get is they don't really understand how to measure the impact of the JVM on their application. They say, well, we've looked at garbage collection logs and we've kind of tried to analyze that, but we can't really kind of work out what the impact is. So we've created this very simple tool called JHiccup. And JHiccup is designed to measure the effect of the JVM and everything below it on your application without interfering with your application. We run a thread in the same JVM as your application, but we don't actually use that thread to interact with your code at all. So you don't make any changes, we don't interact with your code at all, we just simply have one thread that runs alongside your application. That thread spends most of its time asleep, so it doesn't even interfere with the performance of your application. When we start up that thread, it says, okay, I'm going to go to sleep for 1 millisecond. When it wakes up, it looks at the system clock and it says, what time actually is it compared to when I thought I was going to wake up? So you've got nanosecond resolution, so even if it's a very small amount of time, you can measure that. But typically what you'll find is if you're running on the hotspot and you have a big garbage collection pause, clearly, you know, that 1 millisecond can turn into 200 milliseconds or 2 seconds or 2 minutes or a day and a half if you're really unlucky. Then, by recording the difference in time, we can measure what impact the virtual machine is having on your application as it runs. From that, we generate some log files, we generate some histograms, and then we can plot a nice little graph. So this is a good example of something that we see with different virtual machines. So this is a Cassandra node running with a 60 gigabyte heap. And on the left, we've got the application running with Hotspot, and on the right, we've got the application running with Zing. So if we look at the top graph here, this is just monitoring the difference in time. So this is the latency that we're seeing from the virtual machine. So probably hard to see it from where you're sitting, but there's a scale on the left here, which means it goes up to about 550 milliseconds. So there's a big pause at the beginning, which goes up to about half a second, and then we can see there's garbage collection pauses fairly regularly in the 100 millisecond range. So it's not too bad, but you know, if you're looking for low latency, 100 milliseconds is not really very good. Zing, boom, just completely drops off. So it's very difficult to see where the pauses are on the scale that we've got there. We use the same scale to show just how big the difference is. If you really want to see it, we kind of expand the scale so you can see exactly how it works. The bottom graph shows percentiles. So if you're looking at a service level agreement where you say, okay, my system has to respond within 50 milliseconds, 99.99% of the time, that's very easy to see on that graph. And again, with Zing, it just goes flatline. So this completely eliminates the problem of garbage collection in terms of pauses. Let's talk about throughput. If we're doing stream processing, as I said, what we want to do is compute-intensive work. We need lots of threads. We need to get lots of things done. Using the JIT compiler and improving things from that point of view is a good idea. So there's different ways of doing compilation. There's JIT compilation, but there's also AOT, ahead-of-time compilation. And a lot of people say to me, well, wouldn't it just be easier if we took our Java code and we treated it like C and C++, and we compiled it into native instructions? Wouldn't that make it faster? And the answer is, well, yes, it would. It would make it faster than interpreted code. But there's a lot of things you can't do with static compilation that JIT compilers can do. Java, for example, is not a dynamically typed language, but it is possible to load classes at runtime. Because you can load classes at runtime, you can't do certain things like method inlining in static compilation because you can't guarantee that the method that you're inlining is going to be the one that gets used at runtime. So static compilation can't do these kind of optimizations. You have to do them with JIT compilation. So JIT compilation is really good. It has a complete picture of all the classes that are loaded. It can do a lot more aggressive optimizations based on the information it's got from the profiling. It can do method inlining, escape analysis, all sorts of things like that. So what we decided was that we would replace the C2 compiler. C2's been around for a long, long time. It came in 1998, so it's literally 20 years old. And if you look at the code, it is literally a ball of string. It's horrible in terms of trying to maintain it. Trying to add new features is even worse. So we thought, right, let's start again from scratch and have a nice clean design. And we looked around and we said, is there anybody doing work in this area that we could sort of start using as a starting point? And we found this project called LLVM. It used to be called the Low Latency Virtual Machine. But it's really a compiler project. It's designed to give you compiler modules that you can put together for different projects. And there's all sorts of people involved in this. There's Microsoft, there's Intel, there's AMD, there's NVIDIA, there's Sony, there's ARM. All the people who understand like chip architectures and how to write compilers are working on this project. So we thought, okay, that's a really good place to start. But most of what they've been doing is ahead of time static compilation. So we took the work, we integrated it into the JVM, so it worked in conjunction with things like garbage collector, worked with thread synchronization and stuff like that, and we were then able to use it as part of the JIT compilation system in the JVM. That gives us better performance. The other thing that we wanted to do was to look at how to deal with this warm-up phase. So that the fact that we have to wait a long time to get to a point where we can actually run our application at full speed. That could take a few seconds, it could take a couple of minutes. For certain applications, that really doesn't matter. If you're just running a web server, if it takes 30 seconds or a couple of minutes to come up to full speed, nobody's really going to be too upset. But if you're running some kind of trading system, or a system, even something like a microservices architecture where you want to spin up new instances of a service very quickly to adjust to changing loads, then you don't want a delay to get to the level of performance which is 100%. So we thought to ourselves, okay, how can we solve that problem? And the idea is ready now. So again, when I talk to customers and people about this, they say, well, why can't I just take a snapshot of all the compiled code once the application's warmed up? And then when I start the application again, I just reload that snapshot of all the code and off I go. And the answer is you can't do that because there's certain rules about how the JVM must start up. And there's also a variety of problems about how the code that you've compiled may not match the way that the code is running at that particular time when you start up your application. So with Ready Now, what we do is we say, at some point after you've run your application for a while, record a profile. And the profile contains 4 things. It contains all of the classes that are loaded at that point. It contains all the classes that are initialized at that point, because that could be 2 different lists. And then it contains all the profiling information that's being collected whilst the application has warmed up. So it knows all the different things that were gathered, and it knows where a speculative optimization proved to be a mistake. So it optimized based on a certain assumption, that assumption was wrong, and it had to undo the code. So by recording that information, we can then use that when we start the JVM up, and we can say, okay, load all those classes, initialize all those classes, use the information from profiling, use the information about the speculative optimizations that didn't work, and recompile the code at that point. So you recompile all the code right at the beginning, and you get to an optimum level of performance much, much more quickly. Literally, the thing is with this, we can gather information over a much longer time. You don't have to just wait until you've done your warm-up for 15 seconds or 2 minutes. You can let it run for a day, you can let it run for a week, and then take a profile. So you get lots of good profiling information about a real application. And then you can use this code to initialize your classes, you can recompile classes, and by the time you get to your public static void main, literally all the code is compiled. And that way, if you're running like a trading system, you start your trading system a few minutes before the bell of the trading day starts, and you're running at full speed. If we look at the effect that can have, then the orange line here represents a typical application where you go through this up and down idea of optimizing to find that level of performance and throwing away optimizations because they're wrong and doing things like that. Using Ready Now, we go straight away into a very flat line in terms of latency, so you immediately get that level of performance that you want. The other thing we're doing as a sort of research at the moment, this is not in the product yet, is compile stashing. Compile stashing is basically doing what I told you couldn't do, which is where you take a snapshot of the code that you have at a running application, and then you reload it when you want to restart your application. But it does work slightly differently, because what we do is, again, it's all about optimizing around speculative optimizations. What we do is we stash compiled code. When you compile a method, we keep that method's compiled code, but we also make like a fingerprint for that method. Because it's not just about the method being compiled, it's about the method being compiled and the information that was recorded, the profiling information for that particular compilation. So in effect, what we can do is we can say, okay, when the JVM wants to have a compiled method, it goes to the stash and says, is there a compiled method of this name with this profile? And if the profile and the name matches, then we get back what's in cache. If it doesn't, so even if it's the same name, but it doesn't match the profile, then we go to the JIT and we get it compiled based on that. So it's a way of improving even further the speed at which we can bring up services and get things to work as quickly as possible. So just to summarise, going back to the graph that we saw earlier, we have the old style of doing things. So we have a long warm-up, we have the optimizations, we have garbage collection pauses. What Zing does is eliminate garbage collection pauses by using C4. So we do away with the idea of long pauses to stop application threads and do garbage collection work. Then Falcon is the idea of raising the level at which we can optimize our code too. So we get a higher level of performance. And then Ready Now is about pushing that envelope so we eliminate the problem of the warm-up phase and we get a much shorter. So we're getting to that ideal graph that we saw at the beginning where it's almost to the point where it starts off at 100% and just maintains a nice flat line. So we're almost there. So Zing JVM, the idea is we start fast, we go faster, and we stay fast. As I said, it is a simple replacement for other JVMs. You don't have to recode anything, you don't have to change a lot of configuration and things like that. So all you do is you install Zing, change your Java home environment variable, change your path, point at the JVM, and off you go. You can try it free for 30 days. You can go to azul.com/Zing trial, and you can download it, you can try it, see if you like it, see if it solves your problem, use JHiccup, compare the latency of hotspot or what the JVM you're using at the time against Zing with the same application. The other thing is Zulu JVM. So this is the other side of our business. So I'm not going to spend a lot of time talking about this, but this is a straight build of OpenJDK. So it's not changing the garbage collector, it's not changing the JIT compiler, it is just exactly the same as OpenJDK. Why do we do that? Well, the idea is to have a cost-effective alternative to the hotspot JVM and JDK that you get from Oracle. The reason for that is that there are big changes happening in terms of the way that Java is delivered, the way that Java is deployed, the availability of updates. Oracle are now creating a new version of Java every 6 months. JDK 9 came out in September last year, JDK 10 came out in March this year, JDK 11 is going to come out in September this year. So every 6 months, a new JDK. Oracle have said that some of those releases, every 3 years, they're going to have a long-term support release. So everybody's getting very excited and saying, oh, JDK 11 is a long-term support release, so we're going to go from JDK 8 to JDK 11. The thing is that the long-term support releases are not free. If you want to use the long-term support release where you get updates for more than 6 months, then you're going to have a commercial support contract. And in fact, Oracle just literally today have announced a new pricing structure for how you can do a subscription model for the JVM and the JDK. So if you want to carry on using Java for free, you're going to have to change your JDK every 6 months. In terms of the Zulu JVM, we're offering a support contract around that at a very much reduced cost compared to Oracle. So with that, actually I don't think I have time for questions now, so we're going to move on to the next presenter.
Our next speaker this evening was formerly a Java developer and IT architect at IBM. Please welcome the co-founder and VP of Tech Operations for Hazelcast. I'm going to mess up his name. I'm going to try not to. Fuad Malikov.
Good enough. Good enough. Thank you, guys. Before we start, let me just ask the audience: how many of you have used Hazelcast in-memory data grid or Hazelcast JET before? Okay, 1, 2, 3, 4. Okay. How many of you have used any other in-memory data grid before? Okay, cool. And how many of you have used any distributed cache before? Like Redis, Memcache? Okay, a couple of more. All right, good. How many of you used any stream processing before? Like Spark, Storm? Okay, good, awesome. Well, thank you. Okay, So today we're going to talk about Hazelcast JIT, which we call is its third generation stream processing engine. And the reason we call it third, because the first generation was Hadoop, second generation was, things like Spark, where it started, to do the batch processing in memory. And the third generation, we call it the engines that can do both stream and batch processing as a first level citizen and be really effective of that. So we think, JIT is one of them, and that's our aim. So, one of the questions earlier was what a DAG stands for. It stands for Distributed Acyclic Graph. It has nothing to do with graph, processing or graph engines. It is basically a representation of the processes as a DAG. Okay, and Hazelcast is basically built on Hazelcast JIT is built on top of that concept. So before we go into Hazelcast JIT, let me give you like a very brief history of Hazelcast. Hazelcast started as a in-memory data grid product, and it's the first line of code was written in 2008, and it's been up there. It's open source, Apache license. I think our latest number is about 55 million Hazelcast servers starts every month, somewhere around the world. Now, for those of you to understand what Hazelcast is, think of a hash map, right? When we asked about the Java developers, half of the people's hand went up. So think of a hash map that normally sits in a single machine's memory, right? Where it's a key value store. You have key, you have value, you store it in there. Hazelcast took that hash map and distributed it into multiple machines. So now you can access from multiple JVMs the same hash map. So if you just copy paste it and and compile it and run on with Java 6+, this will run. It will start a Hazelcast running. If you do it again and again on multiple machines, they all will be eventually pointing to the same map. Okay, so one JVM can update that, and another JVM can see the updated value. So this allows us to store large amount of data in memory using Hazelcast. So normally, you would be constrained with your single machine here, but allowing this one, now you have ability to store, to shard that data. Let's say if you can store 1 million entries in a single machine, you can store 10 million across 10 machines with Hazelcast. No need for anything else. That's the only thing you will need to run it. Okay? So Hazelcast JIT is built on top of this. So it's a stream engine that comes with in-memory storage. So any other framework out there usually requires an external storage system to store it, even in memory or in disk. Hazelcast JIT comes with Hazelcast built in. Now the simplicity that we were able to achieve within Hazelcast in memory data grid, we wanted to follow that with JIT as well. Okay? So now, again, we actually started to work on JIT in 2015. It was an experimental project. And in February 2017, we released the first version. The final version that we publicly released is 0.6. 0.7 is in development right now. It's a single jar file that's about 10 megabyte, does not have any external dependency, and that's the only thing you need to run it. It requires JDK 8, unlike JDK 6, where for Hazelcast in-memory data grid. And as I said earlier, it supports both batch and stream processing. And we'll talk a little bit more about what that means and and have examples, and hopefully I'll have a demo as well. So again, what we mean in distributed, we mean an engine that can run on multiple servers. It's high available, right? It can survive node failures. It can scale as you add servers, right? So you can use all the memory and CPU resources available on all those machines, right? And obviously no single point of failure. Of course, nowadays, for example, what I see, a lot of companies is trying to go into cloud, right? Being it AWS, Microsoft Azure, or Google Cloud. And the common thing you find there is a commodity hardware, right? There's a lot of them. So you need systems that can scale horizontally, right? So both Hazelcast product actually is able to do that. So a very high-level view of what a jet does. I think it's a nice picture. So jet is an engine that can read from any source. Okay, these source could be a file system, HDFS, Kafka for streaming, a database, or any custom source that you can implement on your own. It can process it. It can do things like transformation, filter, joins, aggregations. It can enrich that data that is coming through it using Hazelcast or other sources, and then it can output the result into, again, sources similar or syncs similar to that. It could be Kafka, it could be file, it could be Hazelcast in memory data grid, it could be notification of a REST endpoint. You can do any of that. Yeah. So let's talk about the DAG-based processing a little bit, okay? So I mentioned that JET is a DAG-based engine, okay? And here's what it means. So this is an example of a DAG. Has two sources, A and G, right? In our context, we represent the vertices as processing units, right? As the computation units. And the edges are the links between them. You do the A first, and then the output of A goes to B, and B, notifies C and D, whatever it does. So that's our representation. And now, normally, it's actually, you guys all heard about MapReduce. MapReduce is a very simple DAG representation, right? And then Spark came on top of that, kind of extended that concept, stored the results of each process in memory, so it became very fast instead of writing to HDFS for the next process to pick it up. And the other systems that are based on DAG are things like Flame, Apache Tez, Storm, Spark, and JET is based on the same concept as well. Now, let's run through a simple example, and then I'm going to ask you guys. So let's imagine we want to do a word count. Okay, it's a very simplistic MapReduce example typically given. First, I was really objecting to that. Let's come up with another examples. But then I realized that it's really simple to explain things, right? And when you run performance numbers, it really shows you the performance numbers of the engine itself rather than any complex computation that you might be doing with it. So that's why it's a really good example, and we'll keep with that. So let's say you have a source, you have a file with a lot of text in it, right? And you want to do simple word count and figure out the most commonly used 10 words. So how would you do that? Any way of doing it in a very simplistic version? Anyone? We're out of t-shirts, but Yes.
Your hash map, word is a key name.
Yes, that's a very good one. Yes, so just iterate through your text, right? Create a hash map, parse it obviously first, and then start with 0, and as you find more, start increasing that value, which will be the counter. Now later on, you have to go back and sort it based on the count, based on the value, right? And then that would be good, one way of doing that. And that's exactly what this is describes. So, a code for that, in Java would be something like this, right? Have a map, iterate through your source, which is text here. Now, this is, uses Java 8 API, but what it says is, start with 1, and then as you have, the same entry overlapping into the hash map, then add +1 to that. So, basically what you just said. Now, this is great. And to visualize it as a DAG, here's what it would look like, right? The source, we have our text file. First, what we need to do is we need to tokenize that, right? It's a text. We need to get the words. We need to find the words in that string. And then we need to aggregate. Every word needs to be aggregated in the same place. And our aggregation function is just add 1, right? Increment 1 as you find any matching word. And then the result is stored in a hash map, right? That's our sink. Now let's look back into this code. What can you optimize here? What is bad about this code? it's a single threaded, right? It's sequential. Like if we have a very large text, right, where we could actually have multiple threads doing this counting on multiple parts of that string or of that text, of that source. And, of course, this is a hash map. It's not thread safe, but we could use a concurrent hash map, and we could do this concurrently. So that would be much better. So indeed, we could actually create for each process, we could create like a queue for each process and parallelize that. So instead of having one tokenizer, we could have, multiple tokenizers. And sort of split the source into multiple tokenizers. And then instead of having one aggregator, we could also split that into multiple aggregators, right? So, for example, just to make it simple, word New York could be aggregated here, word San Francisco could be aggregated here, and similarly, you basically have a better scaling system, right? Now, to go even further, we could actually even split the source, right? Previously we tried to, given a static source, we want to make the computation as fast as possible. But now imagine you can't even split the source. Like imagine our source being a Hadoop distributed file system. So it's already distributed. It's not in a single place. So we can have one node running on one partition, another node running on another partition. If this is Kafka, it could be one partition processed with one node, another partition processed another node. If that was your source is Hazelcast, and as I described earlier, Hazelcast is memory data grid, it's already partitioned. So, it's the data that we store is partitioned to the servers. So one node could be processing one partition and the other node could be processing another partition. Now here, of course, the trickier part would be, now notice that I added one more step here because the first accumulation is going to be in memory. The second accumulation needs to be global accumulation because some of the words will be here and here. Eventually, we need to merge them together to find the global value, right? So we add this extra step where now we can be actually doing a distributed vertices or edges. Yes. Any questions so far? Are we good? Did I lose any of you? No. Okay. Perfect. So let's talk a little bit about the performance because the reason we actually designed JET because of the performance. We want something that is extremely fast, extremely simple to use, has low latency, and and better than what's offered in the market. So, and as I said earlier, you can use JET for two reasons: batch processing and stream processing. Who can tell me what's the difference between those two?
End of day versus real time?
Say it again?
End of day versus real time?
Yeah, that's a good example. Yeah, the batch processing, you have data sitting somewhere, right? Typically it's in analytical use cases, end of the day, or even, you run some sort of a query, you wait for the result, it's available, then you consume that. Whereas in a stream processing, the data is going through you real time, and you want to do some sort of computation as it passes through you, right? It's more, and in a batch processing, you are focused on throughput. You want to be able to process as much data as possible. In a stream processing, you are more focused on the latency. You want to get the result as soon as possible, right? So we did a word count benchmark against, some of the usual suspects, and the blue line is the JET reads from HDFS, and the same with the others. Now the green line is JET reading from Hazelcast, meaning that in memory. So because Hazelcast JET comes with IMDG bundled in, so this shows how much performance you can gain by putting your data in memory and processing data through memory versus traditionally, starting with an HDFS. So it's not necessarily apple-to-apple comparison, but it should give you some idea. But as an apple-to-apple comparison, you can see that Hazelcast JET's throughput is superior than the other products out there. And then we did the same thing for stream processing and implemented again streaming trade monitor. Now here the key is, so the question to you, how do you count an infinite number of data? Or infinitely, streaming data?
You don't bucket just take a screenshot of this particular time. Like if for lab this was
Okay, yeah. Another way of saying that?
Per second.
Per?
Windows.
Yeah, windows. Yes, you define windows, right? So because it's continuous, it doesn't make sense to count it globally. What do you define windows? How many trades am I doing per second? What is my biggest win in the last second, right? So now of course there are different type of windows. There is tumbling windows, there is sliding windows, there is windows as much as you want. And here an example of a tumbling window, and number of messages per second is different, so you get more and more load on the system. And as you see, now here the criteria is, at the end of the window, how fast can I get my aggregation result, right? That's the key point. That's why we are measuring the latency here. And as you see, no matter how much messages per second you have, Hazelcast JIT is always fastest. And some products have issues with number of messages per second increase. Okay, so that's some numbers. So let's talk about. I mean, I can't go as deep as Simon did. I mean, it's going into the deeps of the JVM and making it work fast is a science, and is really great engineering. But when we design JIT, though, we try to make use of. To make it faster, we use things like green threads. We want to optimize a lot of things so that there's less context switch between the threads doing the processing. Make sure that we utilize the CPU level caches as much as possible so that they are hot. They don't have to invalidate them. A typical even though, for example, there's a vertex here, there's another vertex here, this doesn't mean that they are handled by different threads. So Hazelcast will optimize them. As an example here, a single thread might do some task here and then move on to do the second vertex of the same data over here. So the data is in the cache already. So by cache I mean CPU cache. So it doesn't really have to context switch them or invalidate them. And then there is built-in back pressures into the system so that it knows when to stop here and go back and do more of this processing and etc. Now, of course, this is going to run on multiple nodes and multiple threads. They're going to be switching between threads, but again, as much as optimization as possible to make it fast. That is the reason why we get the numbers that are fast. It's not just because because it is, right? So that said, again, we discussed about these. Edges being local, being distributed, being between threads, and here is a high-level API how using the JIT would look like. We defined we call it a pipeline API for the JIT. There are actually 3 different APIs. There's a low-level DAG API, which literally, you create a vertex, you create an edge between vertices, and then you define the parallelization level and etc. It's really low-level. We use that to build the higher-level APIs, but users, of course, welcome to use that, but it's not intended for day-to-day use. On top of that, there's a pipeline API. We are in Hazelcast in-memory data grid. We were inspired by Java interfaces. So like our distributed map implements Java util map. Hazelcast has distributed queue, implements Java util blocking queue. Or we have executor service, implements Java util concurrent executor service interface. Similarly, we actually I'm not talking about that here, we actually started by implementing Java 8 Stream API. However, though, even though the name is called Stream, it's actually suitable for batching API because it doesn't really talk about any windowing or things like that. So we kind of inspired from that, not necessarily implementing the same interface, and we designed a pipeline API that supports both batching and streaming use cases. And for we talk about latency and throughput, and in Hazelcast we have tumbling windows or fixed windows or sliding windows or sessions where defined by the user activity. It could be where if user is active, you keep the session. If not, you close the session. Type of use cases. Just to visualize how things work internally. Let's assume these are the events going through the timeline. And now, note that when we do count things, the event doesn't necessarily, the time here doesn't necessarily mean the machine's timestamp. So you can actually tell Hazelcast, what time to use. So you can extract that information from the event object by telling Hazelcast how to do that. Then, now these events are not actually coming in an order. So when we do, for example, a sliding window here, Hazelcast is able to, reorder them, and you can define a lag, for example. Now notice that, this event came early, this event came pretty late, right? So you can define a lag, and Hazelcast can wait for that lag to close that window, bring all the right events to the right frames, and then through frames it can create you the sliding windows. So we do all that internally. And in terms of, now of course, this wouldn't be useful to use if it's not fault tolerant, because specifically with streaming, you have a, it isn't like you just did query something and you got a result and you're done with that. In a streaming, your application, your job is running continuously, right, until you want to kill it, because the data is just going through. So you want the system to be high available, right, fault tolerant. And we implemented, some guarantees here exactly once, at least once. And we use, Hazelcast to store the, in-memory snapshots. And yeah. Okay, so time for a demo. You guys want this thing to run?
Yes.
Yeah. Okay, so now first thing first, if you go to jet.hazelcast.org, let me take a step back. It's Apache license. Everything I show in Jet, the Jet itself completely is Apache 2 license. It's open source. Feel free to go use it, deploy it, run it. No strings attached. Now, and if you go to jet.hazelcast.org, you'll find all the benchmark information there, all the use cases, and then a link to our GitHub page where you can see the code. And then there is a 2 extra projects. One of them is Jet code samples, where it will give you code samples of how to do X, Y, Z. And then there is Hazelcast Jet demos, which are more standalone applications where you can run and see end-to-end how it works. So I'm going to run 2 of those demos, and the first one is, this actually was designed a couple of months ago where cryptocurrencies were like really hype, and we wanted to see, to do a stream processing where we want to, as a source, it's real-time Twitter. So I'm actually online. Yes, I use my phone to be online there. So it's going to connect to Twitter, and in real time, get the tweets parsed on the cryptocurrencies. And then using a library to do, it's going to use a library to do sentiment analysis. And we'll define whether the message on the Twitter is positive or negative on those cryptocurrencies. So back in the time, it was mostly red and green. Nowadays, it's only red, unfortunately, meaning that it's negative. But let's try that. So again, I've just downloaded code samples, compiled it. It's ready to run. So I'm just going to run it, and hopefully we'll see how it's going. So first thing first, let's see the actually the DAG that is created for that. So if I see it correctly, so it uses the Twitter as a source. It does flat map by parsing that data. It creates a couple of sliding windows. We'll see those. There are 30 seconds, 1 minute, 5 minute sliding windows, and then we'll parse it, apply the analysis. I don't remember exactly which step it does, and then as a source, prints them into 3 different maps, which is displayed over here. So it's real time, and this is the number of tweets it has captured since it's running. You might see that these are increasing as we go. Bitcoin obviously being the most popular one in terms of number of threads. Number of tweets. Ethereum, I think, is the second one. You can see right now. Yeah, as you see, all time to sell your currencies. Okay, so again, code is there. The DAG looks like something like this. Code itself actually have even better visualization of the DAG in terms of the steps, how to do that. Sample code is there. Definitely not a big project in terms of the amount of code to be able to achieve that. Now the second thing we did was also a stream processing use case. I think I'm here. Let me check if this is running. Yeah. Now this is gonna be, I don't remember exactly which website it is. Again, as a source, it's gonna, let me actually run it because it takes time for this guy to collect data. It is gonna connect to a public website where it gives us the actual positions of the airplanes right now in real time. So what we do, we take that information and then we filter out or we filter in only certain cities. Like if it is in a particular distance to certain cities, let's say within 50 miles distance of New York, we consider that to be in the New York area. And then we'll look into the altitude of that plane, whether it's going up or going down, meaning that taking off or landing. And then there is also, now it's an example of how you can enrich the data. Then we have a static, then we take the type of the airplane, and based on that we can determine, or the engine actually that's on the airplane, we can determine the amount of noise that it can generate in terms of sound, and the amount of CO2 it puts out there. So this is more static data. So given a real-time data, we enrich it with this static information, and then we, I have a graph here. Then we plot to see which cities are most polluted in terms of CO2 emission and in terms of the max noise around that airport area. So let's see if New York, and you see there's more activity around New York compared to other hubs like London or Frankfurt. Yeah, unfortunately, New York right now is top in terms of CO2 emission, and as well as in terms of, I think this is New York, in terms of the max noise around the airport. Now, to be honest, I don't know exactly which airport this is in New York, but I assume it includes all three airports around this region. And again, code is available on GitHub, but it kind of want to show you how we can enrich the data. And the DAG for this guy is gonna hopefully, let me see if I can see that. It's something like this in terms of the processing. Again, starts with this source to get the streamed aircraft. It filters based on the location, creates a couple of sliding windows. At one point, it needs to enrich it. Let me see where it does that. Yeah, I don't know where it does that. Anyways, and then writes into a custom sink, which is Grafana, and then that's where I can show you those graphs. Yeah. Well, that was all from my end. Thank you so much. I guess at this point, we're going to have some Q&A session for a couple of minutes, or yeah.
We don't have a long Q&A time, but we could take a few questions. So you're handling it first.
Yes.
How do you compare with Akka?
Well, Akka is mostly an active framework, right? I mean, I assume you can do some certain things with Akka versus with Hazelcast, but this is Hazelcast JET. I've not thought about that because that's the first time I hear that. First of all, JET will have its own memory storage. I don't think Akka has that. Second, Akka is really based on message passing. You could argue that there's also message passing here. Yeah, I don't know what else to say, to be honest. I mean, I've never thought about JET versus Akka. Yeah, what is your thought on that?
Well, I think we have a more complete solution.
Yeah. That's what I think as well. I mean, you can use Akka for build applications like this, but it is a little bit lower level framework than ready to use for streaming or
We also
capture.
like a streamer.
Right. I mean, nowadays actually everyone has a streaming component into it. So
You
yeah.
have a Scala interface?
We do have a Scala interface for this, yes, but it's a wraparound Java. Yeah.
Next question? Yes.
Yes, so in the beginning of the presentation we told that if we create a single map, it can be distributed on different JVM.
Yes.
So suppose we have a microservices and it runs on different instances.
Yes.
So if I keep my sessions in a map, if I create that map, it will automatically be how it make it group like this is my session map and I just in every instance.
Right. Well, when you create Hazelcast in memory data, this is more for Hazelcast in memory data grid question. So when you have a Hazelcast in memory data grid running on, let's say, 10 microservices, right? First, through configuration, you give them a name. Let's say service A. So they form a service A cluster. And then within any instance, if you say Hazelcast get map my map A or my map X, that will be referring to a distributed map that lives on all of them. So any JVM can read and write to that. Imagine it's kind of similar to a table in a shared database, right? Now, if one of them does like map.clear or map.delete or map.remove a key, it is going to affect all of them because they are connected, they are part of a cluster. Of course, I can go deep down into explaining like how they communicate with each other. There's a TCP/IP network connection between all those members. But yeah.
So it can work on dynamic instances.
Yes. And you can let's say you can add 2 more instances, and suddenly your map will grow into 12 instances. And then let's say you don't need them anymore, you can shut them down, it will shrink down, and all dynamic, no need for restart or anything.
Yeah, next question. You had a hand up before? Okay. Yeah, so is that your hand up or you're scratching in a chair?
No, it's both. Where does it break? So I'm just kind of, it seems like it can handle a lot.
Where's it break?
Where's it, like, this is 3 airports, it was 1 billion airports, 10
Good
like,
question,
how
good
much-
question.
Like, how do you break it?
Yeah, at one point it breaks on your CPU cores, right? How much processing power you have. Obviously, these are really small examples in terms of the throughput. I mean, there's only, I don't know how many planes out there. But you can easily scale this, and we run a lot of applications where this can scale to millions of operations per second. Now, the design of it is it's based on distributed and sharding the sources and processing. So, you can, I'm not going to say like you can have thousands of JET nodes. At one point, network will become the bottleneck. It's reliant on TCP/IP connection between the members. That means if you have 1,000 members, that's million TCP/IP connections in the network. So, but in general, you can easily, in Hazelcast and JET, deploy on hundreds of servers. And it's typically, breaking point will be your CPU resources or your memory. In Hazelcast, typically it's memory. It's the amount of Java memory you have. Things like Azul is really helpful here because you can have no GC memory, uses there with larger heap sizes, not breaking, Java a garbage collection. Hazelcast also has something called Hazelcast Enterprise, which we are able to store the data outside of the Java heap to achieve the similar results. So those are the technically breaking points.
That's right, in the middle.
Yeah, so, of course, I work for Hazelcast. Full disclosure.
Loaded question.
So we know that Spark is very popular,
Yes.
by a long shot.
Yes.
Assuming someone has a new product, why would they think of using JET as opposed to Spark? What are some things they may find that are different?
Right. I mean, Spark is one of the biggest Apache projects, and they have a lot of, machine learning libraries and etc., which we don't have yet. Now, on the JET side, if there's a specifically new project, it's only 10 megabyte, doesn't have any resource. You can embed it within your application. You don't have to deploy a Spark. You don't have to, do a bigger project. We've seen a lot of cases where it's more operationally, it's costly to operate, large systems like that in production. So JET is much more lighter than that. Now, for people like data scientists, I think JET doesn't address some of the questions yet because it's more of a developer-friendly tool right now versus being, UI or data scientist-oriented library. But if you're a Java developer specifically, or Scala developer, and you're building, very low latency stream processing engine that you want to, low footprint and faster performance JIT is a very good candidate. Plus, again, it comes with its own storage system, so you don't have to think about that. Typically with others, you have to have somewhere else to store either intermediate results or share results between multiple jobs, stuff like that.
Before we take our last question, I want to remind everybody we are giving away an Apple HomePod in just a few minutes. In order to win it, your business card must be in this metal tin. If you have not done that already, this is your last chance. We're not going to wait when it comes time to draw. We're going to take the last question, then we're going to do the drawing. Last question?
Of course.
Hands?
Any question for the
Simon
early
Ritter.
for Simon?
Going once, yes.
Which systems do you see as your competitors? Is it Spark and Flink, or where is that niche that we're trying to squeeze in?
Yeah, good question. I mean, first of all, it's really designed around, when we first started this, we were focused on people who already use Hazelcast. So very common use cases were loading data into Hazelcast or processing data that's in Hazelcast. So that's how we started. And then people approached us and said, well, I have this Spark job that I was doing that. Can I do it faster with JIT? So, we start to address those use cases. So to answer your question, right now, we are not addressing the data scientists and machine learning, users of Spark. We are addressing the developers who want to build really fast streaming use cases.
I'm out in the field locally here. So we're seeing clients come to us and say, we want to build a dashboard. I want to be able to get real-time data on my portfolio or P&L, right? It's not machine learning. This is just, give me my data and I want low latency information. I want to know how much money I'm making now, not 2 days ago.
Yeah, I never implied any machine learning dependence in my question.
Right.
I'm not sure why you always...
Well, because that's why I think because Spark's been around for a while, it's accumulated a lot more
Right,
functionality.
but Spark is not for machine learning just. I mean, the use cases for Spark are only 99% of outside of machine learning. And even in machine learning, I mean, Spark does very little because every serious data scientist basically works with numerous Python, packages and not with Spark.
Right.
Spark does not implement almost anything.
Mm-hmm. So what would you say? From what you're...
Well, I don't know. That's why I asked the question. But not just
I
Spark,
know,
but any other. So we know that there are all of these kind of generations
Right.
of streaming systems.
Right.
Started with Spark, which is not really streaming
So let's just
systems,
say-
but Flink and Apex and Google, Dataflow and others. Do you see yourself as a competitor to those things, or you are in some other
I
place?
think when we see you're enabling the faster adoption of stream processing because we make it easy. You can implement it, embed it in your application without having to make your CIO make a big decision around what is going to be my stream processor for my company. Right? You have to stand out with big infrastructure and put it right in your application.
But
What about Kafka Streams in this case?
Kafka Streams is also...
My application.
Yeah, absolutely. But you correct me. But Kafka Streams would work with Kafka as a source,
Yeah.
and with JIT you can use Kafka as a source and many other sources as well. So yeah. I mean,
It's a obligatory phenomenon. So I haven't. I'm talking about stream processing.
yeah.
We're talking about stream processing without
Yeah.
Kafka.
Well, I did say that a lot of people have now stream processing. So yeah, to answer your question, I think yes, we consider us as a competitor to Spark, Flink, and as you saw, our benchmarks were against them. So it isn't like we don't see that, right? Now the things that we are focusing on is low footprint, better performance, true stream processing versus micro batching and things like that, and fast application development right now without much dependency. And one thing that Hazelcast JIT can do a lot is being embedded into your application. So you don't have to have a Spark running somewhere else. You can just have your application having the power of doing stream processing without deploying something else. And we've seen that really welcoming in Hazelcast before, how people really like that, how easy it was for other vendors to build applications, or suddenly to make their existing applications super powerful. The term back then used to be, I make my application cloud ready using Hazelcast and memory data grade, because I just added Hazelcast jar and suddenly it's cloud ready, it's scalable, you can add in remote servers. Now that same term means way more. It means something else right now. But we want to give the same ability with JET to the users. However, though, it is still a relatively early project. So one of the goals, me being here and talking to you guys, is to give you an idea of what it is, what can be done, and then hopefully see some of you guys going and trying giving us feedback and saying that this part of it is really good. I found it very useful. That part I think sucks, and here's what you should do, and and that's how we make Hazelcast today, and I think that's the way of making JET as well.
Okay, that is all the time we have for Q&A. However, Fuad and Simon are here for one-on-one questions right after our raffle. Thank you, Simon and Fuad. I know you clapped already, it's okay. All right, the next thing we're going to do is give away this Apple HomePod. Let's see. Can I ask you to reach in and mix this all up?
Before I unplug this, do you want to do your magic? Or
Just
can I
leave it go.
unplug it?
Leave it go. Don't unplug it.
Oh,
Just
okay.
leave it
All
on.
right, I'm leaving. Okay.
Okay, let's see. Can I ask, don't look away, I'm coming to you. Can I ask you to reach in, look that way, and reach in, pull something out? All right, and no, you're going to read it out. Read it out. I don't know what it says.
That's my name, you know that, right?
You can't win, sorry. Michael Echeverry. Anybody? No, you just gotta raise your hand. I'll just clap for him. If he ain't here, he ain't winning. All right, pull out another one. Go for it.
Suspense is on.
Read it out.
Karen Mo.
Again, our speakers are here for one-on-one questions. Come up now and ask. Thank you all for coming.